So now, if you want to decide whether a formula is valid, i.e. it's true in every universe, or I guess whether it's true in our, then I'm going to give an algorithm for it, but it's going to be an infinite time algorithm. All right. So, so what is, an algorithm, you have a precondition, what's true about the input, postcondition, what's true about the postcondition, right? So our input is we have some predicate logic formula, and we're going to output whether it's true or false, right? And our frustrated guy, of course, says, hey, you can't, it's an undecidable problem. There's no algorithm for deciding whether it's true or false. And he says, yeah, it's not really an algorithm because the algorithm could take infinite time, right? And he said, well, then it's not really an algorithm, is it? But anyway, here are two settings of alpha, right? And when I leave it blank, it means, right, it could be all those other settings could be true or false. We don't care. And you've seen already, this one says that there exists one girl such that for every boy, that girl is loved. And how does this kind of work as an algorithm? It says there exists one girl. So how do we find that girl? Well, we can loop over all girls, waiting until we find one girl that has the right property. So this code here is saying, check all girls, and if you find a girl with the right property, then we're happy, right? Now, what's the property that we're looking for? Inside of here is we're claiming all boys. So within the loop, when we have a particular girl in mind, right? What do we do for that girl in mind? For that girl we have in mind, we check every possible boy. But now, in order for us to return true, it has to be true for all of these boys, right? And then you do your little, for each, now you have a boy-girl pair and you check. And you see both of these, this one here will pass the test, right? Because you'll loop over all girls, you'll come to Marilyn Monroe, and when you're doing Marilyn Monroe, the test will pass. Why will it pass? Because when you loop over all boys, it'll be true for all of those boys, right? Well, it'll fail for this girl, this one. All right, so now what about here? We turn the quantifiers around. So now we loop over every boy, looking for a boy in which the statement is true. We loop over all boys, checking to make sure that it's true for every boy, right? This loop will return true if it's true for every boy. And what are we checking? Given a particular boy, what are we checking? We're checking that we're going to loop over all girls and see if we can find a girl, right? So what's going to happen in this code? We start with this boy and we find that girl. So we're happy. This boy, we find that girl, so we're happy. Every boy, we find some girl. So because we succeeded for every boy we found a girl, we'll be happy. Right? Everybody buy that? So and we would be happy, and both of these would be happy, right? Here, for every boy, we would find some girl. This is how you write it up in Eiffel. My friend Chester gave me that code. All right, so here's how you write it up in AND gates and OR gates. All right, so remember we did AND gates and OR gates when we were doing predicates. And so here what we're doing is the top, this thing is going to, at every leaf, we have here are all the tuples. Remember we did the tuple thing. For every value of boy and for every girl, we have a tuple. And for each of those tuples, we check, right? And then when we have a particular boy, right, we have a particular boy, and that boy, we have a particular girl, we check. And then for a particular girl, we do an and over the boys, right? So this is going to return true if it's true for all boys, right? Here, when we have a particular girl said Marilyn Monroe, we do an and over all boys. And if it's true for all the boys, then this returns a true. So when we put Marilyn Monroe on this guy, it returns true. But when we put a different girl, it's going to return false, right? And then after you've done that for every girl, we return the or of those, right? So we say,
is this upside down? Sorry.
Yeah, it's upside down from what we did last time. There's not a universal way in which you build these things.
Oh yeah, I can recall that. Thank you.
Yeah, so the output is going up.
Sir, is it usually a good idea to think of exist statements as ors and for alls as ands? Is that
That's an absolutely great thing to think of, right? Yeah, exists or so here's the reverse, right? Here we're given a particular boy, we try all girls and see, is there a girl that is loved by that boy, right? And so that's an or, and then we take an and of all of those, right? Does that make sense? Here's a bigger version of it, right? We choose the objects left to right, right? We choose we follow some path down this, right? We choose some value for, I guess this is why I drew it this way, is because I'm thinking about, I'm following some path down the tree. I choose some value of W, then I choose some value of X, then I choose some value of Y, then I choose some value of Z. And then we test to see whether F is true for those four objects, right? And then after you do that for all the leaves, then we'll have values bubble up, right? That over all the Zs, we do an or, right? Then over all the Ys, we do an and. Then over all the X, we do an or. Then over all the Ws, we do an and, right? Does that make sense? All right, so here's a game tree. I didn't think we were doing game trees so soon, but game trees are definitely drawn this way. And so I guess that's why I was trying to be consistent. And this is a game in which it's first the white player's turn. Say you're playing chess, any game, right? You're playing tic-tac-toe. We put up at the root who gets to go first. And Mr. White gets to go first. And these edges tell me what move Mr. White can choose. He chooses how to move. And then Mrs. Black maybe gets to choose how they move. And then White gets to choose how they move. And then Black gets to choose how they move, right? And so a path down this tree is a playing of the game. And it's a two-move. In this game, it's a two-move game, right? White moves, White chooses a move, then Black chooses a move, then White chooses a move, then Black chooses a move, right? And at the bottom, I put a black star if Black wins, and I put a white star if White wins, right? So this is kind of like it's like when I turned the for all exist thing into a game, right? If we were playing this over as a game, then it's a for all, so the red guy gets to go, right? And here it's an exists, so the blue guy gets to go, right? Does that make sense? And what do they get to choose? What does the red guy choose here? He chooses the value of W. And then what does the blue guy do? He chooses a value of X. And who wins is based on whether the guy at the bottom is true or not. right? So it's the same sort of idea of this game tree. All right.